Okay. So good morning, everybody. So we are going to continue with our statistical models class. And we're going to start slowly today talking about random variables and probability distributions. And I'm gonna talk a little bit about some things that Paulo already mentioned yesterday. And we have a long class, so maybe we have tomorrow a lab. So if at the end of the class there are a couple of concepts, we can talk about them tomorrow during the lab. So today's key concepts are related to some topics that you may have already studied during your undergrad studies or graduate studies. We're going to talk about random variables and about discrete and continuous random variables and some of their key properties, some of the distributions and some of their key properties. As we mentioned yesterday, the idea is not to be necessarily an expert in the underlying mathematical functions behind this. We aim that you become good users of such functions and that you can think about your own problems and about your own samplings. So there are some parts of the math that if any one of you wants to go deeper, you can go home. It's not a difficult material to find, but we're going to be thinking about what we are measuring and what distribution to choose in different settings. So it's more like from the user side rather than the mathematical side. When we measure data, our empirical data, and I am here talking about something that Paulo mentioned yesterday. When we measure things in nature, when we measure variables, we measure quantities in nature, and we are assuming random and independent sampling for each variable. Sometimes we know the possible outcomes of the variable. We have a notion. Sometimes it's a notion informed by common sense, such as the height of a person. Sometimes it's a notion informed by theory. So sometimes you make measurements and you have a preconceived notion of what is the sample space, what is the interval of possible outcomes that your measurement will take. Sometimes you don't have this. Sometimes you measure something that you don't know what the value will be. In any case, these measurements that we take in nature, even if you know the possible outcomes, all the possible outcomes, a single measurement, the outcome of a single trial of a single measurement is something that you don't know. It's something that you cannot predict. It's something that would take an enormous amount of energy or very precise instruments that you won't do, that would be overkill, to know exactly the outcome of one trial. And we don't need this even. And this is why we're talking about the randomness. This is why we're talking about measurements that can be described by random variables. Given enough experiments and trials, and as we measure things, we can start hypothesizing or estimating how often any of these outcomes in the sample space will appear. So we will have a notion of their probability distribution. So which is the number of times that any one of the outcomes will appear in general in the sample space. So when we measure this in empirical data, sometimes we have different types of variables. We can have the presence or absence of a species in a plot. We can have a coin toss, which is the classical, the simplest experiment of such kind. When you toss a coin, you never know what's going to happen, but you know that the outcomes are going to be tails or heads, and you don't know which is the specific outcome. And still, you can do lots of work because you know the distribution of the probability of such trials. The number of individuals in a given sample or in a given area, if the individuals are rare and you're counting them, this is one of the types of variable that you can measure. You can measure lengths, volumes, masses of body parts. And these variables that are measured empirically, they can be formalized mathematically. And when we talk about random variables, it's the mathematical formalization of these kind of measurements. Sometimes when we talk in the field and we say, oh yes, body length, it's a random variable. It's common that in the language, we're talking about the empirical data that we're taking. And that's okay, that's something that will happen. You have the measurement, and the random variable should be the mathematical formalization. So I want you to understand that when we talk about random variables in this context, I will be talking about the theoretical distribution of this kind of variables. But don't be surprised if when in vernacular language, when we're talking about our field, people use random variable as a measurement. It depends a lot on who's speaking, on the context. These random variables can be discrete or continuous, as we already talked, you probably know. And the probability distributions, they have probability distributions. They represent theoretical distributions that were discovered, basically. And they depict how probable is each one of the outcomes. Random variables can be described by parameters. If you have a normal distribution, you know that there's a mean and a variance that are going to be describing. And with these two parameters, you can reconstruct the whole distribution probability. So these are key properties that allow you to understand the kind of distribution that we're talking about. Feel free to interrupt me at any time. And we're going to talk about a couple of distributions. There are tons of mathematical and tons of statistical distributions, and they are used in lots of fields. But when we start in ecology, I will start just by the basics, and we can go deeper depending on what's the content of your own work. Sometimes you start a line of work that requires you to be familiar with more distributions for different reasons. So in this course, even if I am going to talk about the basic, sometimes you will have to sit and think or justify or read about, and when you read a paper, why a certain distribution was chosen. So the simplest experiment, a single coin flip, is called a Bernoulli distribution. And we know that the sum of the probabilities of two outcomes, the sum of probabilities of the outcomes has to be 1. So if you have two only outcomes, you have the probability of successes and the probability of what we would call failures. It's 1 minus this probability. That's something that I don't expect you to. But when we talk about a coin flip, we're talking about P being equal to Q and being equal to 0.5. But this is not necessarily the case. Sometimes you have experiments that have only two unique outcomes, where P is not equal to Q is not equal to 0.5. You can have P equal to 0.8 and therefore Q equal to 0.2. Are we okay with that? So the notation for a Bernoulli distribution is this. So X is approximately modeled by Bernoulli. And the only parameter of such an experiment is P, is the probability of successes. If you already know P, you know Q, you know everything you want to know. But nobody tosses a coin a single moment, a single time. We do repeated trials when we do this kind of things. When we want to see the outcome, we always repeat the toss or the measurement in different samples, assuming it's independent. And this repeatedly sampling is the one that forms a binomial random variable. And the binomial random variable describes the number of successes in a set of n trials. Are we okay with this? So we have an extra parameter, which is n, is the size of the experiment. So how many coin tosses we did. The notation for a binomial distribution is this. It's bin or binomial. Sometimes it's in full words. And as I said before, it's the number of successes x in n trials with a known probability of success. I would like to think that to help you think, like, how do you calculate this probability? And if you have two outcomes and you're repeating the trial, if you have, for example, two outcomes that are repeated and you know that P is the probability of success, how do you calculate the success of two successes in a row? How do you do this? Do you know what would you do if you wanted to know? Excuse me? You multiply them. Okay, he said multiply, but yes. So since they are independent trials, you multiply the probability of these trials. So the probability of x successes is P times P times P times P in a set of n success of x successes. So it's P to the x. Yes. Are we okay? But when you do a series of n trials and you're looking for x successes, you not only have P to the x, you also have a set of trials that were not successful. So you have a number that is n minus x, so the rest of the trials were not successful. And the probability that this happened is the probability of failures, of not having a success, so it's 1 minus P, multiplied by 1 minus P until you reach that number of failures. Are you following me this here? Okay. This happens in different orders, in different ways in this set. You're not only multiplying this once in a long term of successes, in an n number of successes. You can have, if you want 10 successes in n trials, you can have the first 10, the last 10, a long combination, a different combination of how do you take 10 elements from, for example, 25 trials. So when we try to calculate the probability of the number of successes in such a trial, we have to take into account the large amount of times that this could happen. And this in mathematics is called the combinations. So this is the notation for the binomial coefficient. This means, I don't know how you say it in English. N choose x. No, n choose x. X choose n? No. The first one. N choose x. Okay, yes. So you read this in English as n choose x, and it's how many groups of x successes can be taken from a sample of n trials. And that's a large number. This has a formula, and we can do it quickly, just by making a simple multiplication. So I'm going to stop here, and I will invite you to open your R session. Yes? And we're going to do exactly what I told you before. How do I calculate the probability of x successes in a trial of n? So what we will do here, and if you have any kind of question about this code that is here in these slides, we can talk about it a little bit. But basically, while you open your computers, we are defining n. So we are answering a specific question. So for example, 11 successes in 25 trials. And I'm keeping a fair coin here. P equals 0.5. It could be any number. It's just an example. Yes. And what we're going to do is to define the 3 variables of interest in this first line. And this is something that you will do along this course. When you start some modeling, you will be doing you will be defining the parameters or the variables that you're going to be using in the model. So this is something that we're going to start doing. Even if it's a simple example, this is something that you will get used to during the course. Please, everybody say hi to Diogo. He's the third. He's our third instructor. Welcome, Diogo. So we are going to do this all the time. We are going to be defining the variables first and to use some R notation to create what we want to create. So this is a very, very simple example in which the probability is elevated to the times of successes, and I call this P success. And the probability of a failure, I don't really like this success versus failure notation, but I think everybody's understanding. It's at least, it helps you. Is the number of failures elevated to the number, to the rest. Like this is the length of the trial minus the number of successes that you have. And in R, the function that helps you calculate the number of combinations. It will not give you the whole set of combinations. It will not give you a list of things. It will tell you how many combinations there are. Is the function choose. If you have any doubts about how to use R, or if you want to see the help of the function, you can put your cursor, select, for example, the word choose, and click F1, and a help option should open. So anytime that we work in R, you can check the help of the function, either by executing with an interrogation, or by the quickest way is to select and click F1. And I want you to see that this multiplication is equal to the built-in function that R has to calculate this kind of probability. And we have here D by none, and we will see tomorrow a set of functions that R has already built in for this kind of calculation. So you don't have to do this by hand all the time. R is a statistical language, so it will have built-in functions. So in this case, for example, if you want to answer this specific question, you would use the function D by none. You would say the number of successes. You will tell the size of the trial and the probability of success of each independent trial. OK? This should work. I hope everybody is OK. I will just I will let you, yes, type. I still hear. Let me know if you have any comment, anything. Some of you may have lots of experience with R. Depends. Like biologists tend to be acquainted with R quickly in their career, but not everybody. And some of you may like Python more. We are not going to engage in this kind of. We have no problem with Python also, but we are going to be using R for this course. And are we OK? So the D in D by num stands for density. And tomorrow we will talk a little bit about this. Yes, please. Can you have a mic? I am.
Can you repeat to me, please, what is P?
What is?
P.
P is the probability of success of any single trial. You have one experiment, you have a series of experiments that are independent, and the probability of success, in this example, it's 0.5, and it has to be between 0 and 1, but it could vary in any
Thank
setting. You can. Tudo bem? Como você está?
Is the Bernoulli distribution just a special case of the binomial distribution, or?
Yes.
Oh, okay.
Yes, Bernoulli is a special case of the binomial when n is 1 at the end. But you, like, from Bernoulli stands like a whole other, like, there are other consequences. But at the end, if you say that n is equal to 1, you have the same thing. You don't even, like, but it sounds like over here. If you already know P, it can be more complicated than simple. But yes, of course it is. So we are not going to use R a lot today. Tomorrow is going to be, but I wanted you to loosen your fingers, because tomorrow we're going to be using it more. If you have any questions later, we can just continue. And we, of course, we are not used, it's not necessarily the questions that we have. When we have this kind of binomial distributions, we don't want to answer questions like this. This is specific. It's important to understand this kind of logic. But we want to see the distribution along a series of successes. So we can calculate the probability of having n successes, where x here of x successes, where x takes natural numbers values, so 1, 2, n, for every x. So in this case, with the example where n is equal to 25, we can calculate the probability of having 1 success in 25 trials, 2 successes in 25 trials, and so on, until the probability of having 25 successes in 25 trials. How do you think this could, like, if you flip it a coin, what do you think the shape of this will be? Is it when you flip a coin, is it very common to have only 1 success when you flip a coin? Is it common to have only successes? What do you have? What do you tend to have? You have something that has this shape in your mind. So it's asymmetrical, and it stands around a point. But we're talking here in discrete trials. So, but yes, it is a symmetrical distribution. And I want to invite you to do this, like to plot this probability. I put a title because okay, but you can check the code is in our page, and you can copy also the code there. So it's a bit of a macete. How do you say macete in English? But yes, you could copy the code also. And you should get something like this. And what I'm doing here with the lines that I'm plotting is just highlighting the example that we had. So this x and this calculation stands for the last example. And we have this point where the red lines crosses is our result from the last example. So it's something around 0.13. I don't have here. It's 11 successes, 0.13. Okay. You can.
Where in the page is there the code?
In the slides, you have a syllabus and you have probability distributions, and you have the slides.
Okay.
You're welcome. Is there everything okay? I will not dwell a lot in this. But you're going to see this kind of plot a lot, because we are usually we're not interested in one probability only. And why is this made of points? Can anyone tell me why is this made of points? Exactly, because it's discrete. So I don't depict this as a continuous curve. Okay, so it's not an aesthetical choice. we're going to change to another discrete, very used discrete continuous random variable. That is like an extension of how we would do experimental things. Instead of repeating binomial trials, what we do in the field, what we do in our experiments sometimes, is that we go to the field. We take independent samples, independent events, and we count things. We count the number of plants in a given plot. We count the number of insects in a leaf. All my examples are ecology related, I'm sorry, and plants, but yeah. But we count things, and sometimes these things are not are rare. Sometimes you go to a plot and this element that you're looking for in nature is not. So you will have counts, so it's discrete. It will never be negative, of course. But also, when you have something that that is very rare, you're going to find it very sparsely. You're going to find 1, 2, 3 sometimes. You get happy when you get, again, 0, 0, 0. This kind of events, this kind of counts are modeled by what we call a Poisson random variable. So we still assume that sampling is independent. We still assume that what we measure in a plot is not going to interfere in the measurement of the following plot. This has implications in practical life. Things should not be super close. You should have, for example, if you have an observer who tends to count a certain way, you should try to make everybody who's an observer to have the same method. So the sample should be independent, and these numbers should be still random in the sense that you don't know when you go to a plot how many elements you're going to get. It's not that it's random because nobody knows. It's because you don't know when you do the experiment what's going to happen. And the starting point of a count is a distribution. Paulo was telling yesterday, and we were talking about how the normal distribution are deviations from a mean. A Poisson starts with a count. So it's when events are rare, the most frequent elements are low numbers, are 0, 1s, and 2s. And we describe the Poisson discrete distribution with a single parameter, that is lambda, and it's the average number of events per sample, average number of insects in a leaf, specific plants in a plot. There are probably more examples than these two. So the notation is this. When we decide that to use this, we notate this, so X is modeled by Poisson, and the only parameter we need is lambda. Okay. And the probability of observation of a given event. So in this case, X is not the number of successes in a trial, but also the average number, the number of things in the plot that you're measuring. So the probability of getting 1, the probability of getting 2, the probability of getting 3. How you calculate them depends on lambda of this distribution and will be modeled by this. Are we okay? What happens with Poisson? Poisson has not a defined shape. Depending on lambda, when the event is not frequent, it will have a reverse-shaped curve. We're going to see that tomorrow. So in this reverse-shaped curve, the most frequent values are going to be 0, 1, and 2, 0s, 1s, 2s, because the event is rare. And when lambda starts increasing, so the event is more frequent, the curve becomes more symmetrical. The most frequent value increases, and it goes to the right. Yes, and the curve becomes more symmetrical. And when you have very large lambda values, so you have elements that are more and more frequent in your sample, the distribution approaches a normal curve. Tomorrow we're going to play a little bit with this. But still, remember that it's discrete. We are going to be plotting Poisson with points, not curves. This is the last piece of art that we're going to do today, I think. And I wanted, like, I will note here in the quadro, this. So the probability of a count is lambda to the x divided the factorial of x times the exponential of like e to the minus lambda. I don't know how to say these things in English. I have like e to the minus lambda. And we're going to do this in R. We're going to do this. And this is a tiny example for those of you who are not acquainted with R of how to do functions. And we are not going to do a lot of functions, but sometimes we need one because it's quicker to do stuff. Maybe I will take out my disk quadro here. So this. And this is this same expression in code. So I want you to see that. What is the syntax here? We are creating a function. We are assigning it a name. And we are using two parameters, so x and lambda. Lambda is the only thing that we want to have from a Poisson distribution. And x will be the number of events per sample, the average number of events. So we're going to calculate this. We're going to calculate each point of a possible curve. So, and this is exactly what I'm doing. We're defining lambda, and we're saying lambda to the x divided by the factorial of x multiplied by x minus lambda. We're doing it literally, and this is something that we will be doing a lot these weeks. Yes. And I wanted to see something. If you execute only this piece of code, the function, you have nothing. What you have is a function now in your computer. You created the function. To have the function work, you have to execute the function and give it some data. Give it some data. So this, in this second line, I'm executing the function that I created here. And I'm saying, like, give me the probabilities of x equals 0, 1, 2, 3, 4, 5, with lambda equal 1. OK, so this is going to be a vector of values. And I want you to check it with your own eyes. So this should be something that you receive. And if you can plot it. I hope it's large enough for everyone. Does anyone have any doubt about what we're doing here? Is it so far so good? OK. Can we have here?
Yeah, so I wanted to ask a question, but it was before that. I wanted to understand a little better what you meant when you said the probability of an event happening.
It depends on how you define it. Are you talking about Poisson or before?
Poisson.
OK. So in this case of Poisson, our event is a count. So we are going to have a number of presences of whatever entity you're measuring in a given sample, in repeated samples, because we always do. So the probability of having one, so it's the average probability of having like 1 or 2. And lambda describes the average across the samples, the average number of things that you have, of entities. I mean, insects, plants, whatever you're counting. Can you? Paulo can have, yes, a great example.
Well,
Yes.
You can think lambda as the average rate at which something happens. So if you have a forest, you know the average density of trees in this forest. This is the rate at which you expect trees occur in any given area. For example, if you are sampling quadrats of 10 square meters, and you know the density, so Poisson distribution will tell you what's the probability of observing a single tree in this quadrant, two trees, and so on.
Yes.
Okay.
So, thank you. Yes, and you can plot it later or down. Are you okay with this part? I want to see who got to this in peace with R. Can you like raise your hands if everybody's like okay with this part of code? I know that some of you are having trouble installing things, but it's nice to see how we're doing. Okay? Oi.
I think, well, we have a question here. I'm not sure if you explained the D family of functions in R, and I think it's a good time to explain why these two lines will give the same results. I mean.
Okay, with Poisson I didn't give the so in
just
yes,
the
absolutely.
D family for distributions in R.
Yes.
The different D function families.
So in the previous example, I compared our calculation with D binom. And I told you that D stands for density. So we have D binom for binomial, and we will have D poise for Poisson. And this is the functions, the D family of functions. Calculate the density, the probability density. Of these distributions. And in the case of discrete variables, it calculates the probability of having a certain amount of events. In the case of binomial, the probability of having a number of successes in n. And in the case of Poisson, the different values that the Poisson distribution will take with varying x's. So this plot should have something like this shape. You have 0, 1, 2, 3, 4. And you will have, if it's lambda 1, we will have points because it's not a continuous variable. And you will have something like this. Depending, if you vary lambda, the shape will change, as I told you. It will start being a J reverse curve. And it will become more and more symmetrical. And with lambda growing, the lambda, the higher point in this distribution. We're going to watch this tomorrow. But you can now try to reproduce this value, this vector of numbers, by using the Poise function. Sure.
I'm sorry, it's the first time I'm seeing the Poisson distribution, so I would just like to know what are the restrictions to lambda? Like in the binomial distribution, p has to be between 0 and 1. Are there any restrictions to lambda?
No, it has to be positive.
Okay.
It has to be positive.
Okay.
And it does not need to be a natural number. It can be 0. It's a rate parameter. So it can take values that are 0.3, 0.5. You can have, it has to be positive, and that's the only restriction. And it's the Poisson is a distribution that is only described by this parameter. When we talk about the expected values, yes, please. I will come back.
I just wanted to mention that 1 under lambda, 1 divided by lambda is the mean of this distribution. So it can easily be, how to say this, found, I guess, from the data.
Yes, 1 over the lambda. I think it's lambda itself.
It's lambda? Okay, so
1 over lambda.
1 over lambda is the expected value.
The expected.
For all the distributions for the geometric distribution.
Yeah. But yes, the distribution has this Poisson, like the expected value is lambda itself. Yeah. So, and when we talked yesterday about averages being the expected values for distributions, we're talking about averages, we're talking about weighted averages. Because of course, in these kind of distributions, the geometric, the arithmetic mean happens around this, and it does not make any sense to expect values that are in the middle of the distribution if you already know that the probability of some values is higher. So it's not an average, it's a weighted average. So for all the discrete variables, actually for all variables, you have every value weighted by its distribution. In the case of Bernoulli, this value is p. In the case of binomial, the binomial distribution, this value is n times p. And in the case of Poisson, it's lambda. I will not dwell into the mathematical details, but this is something that you can, if you want to play, if you want to check, if you want to read. This is the expected value of discrete variables. Does anyone have a comment? Does anyone have a question? Paulo, Inacio, and Diogo, if you want to say anything, please.
Well, in the beginning, I think I do not understand the difference between Bernoulli and binomial. Because you said that binomial is a probability distribution of Bernoulli random variables. I think I understood that, and I'm not sure what is it.
Binomial comes from Bernoulli variables, but it measures the times that successes happen in trials. So it stems directly from it. A binomial distribution is obtained when you repeat Bernoulli trials, so single coin toss. But the exact phrasing that you're using, I don't think
but
it's
no, the Bernoulli distribution, what does it tell us?
It's the number of successes in n trials.
So the Bernoulli is describing something that has 2 outcomes, right? That's the idea. You're going to choose between 2 outcomes with certain probability for each outcome. That's the definition of the Bernoulli, right? If you do this several times, then you can get the binomial, right? So if you do several Bernoullis in a row, you can ask, in these repeated trials with only 2 options per outcome, how many of each outcome did I get in the end? And the distribution of this aggregate set, like how many successes that I have over repeated trials, is the binomial. Mm-hmm. So crucially, the Bernoulli is going to output either a success or a trial, while the binomial is going to output a number, right? It's going to be the number of trials that are successes. Mm-hmm. So if you sample from a Bernoulli, you either get 0 or 1. If you sample from the binomial, you get a number between 0 and the number of trials, right? That's basically it. So you can think of the binomial as a repeated Bernoulli.
Yeah. So in our example, the single coin toss, P, is 0.5. The expected value for this Bernoulli is 0.5. In the example that we did before, the binomial, we had n was equal to 25, and P was still a coin toss. So the expected value is going to be 25 times 0.5. So it's going to be 12.5. And it's interesting because you don't even know, like 12.5 is something that you will never get in real life. You will never get 12.5 successes. You will only have 11 or 12 or 13, but still your expected value is around, and your distribution is around this value. Okay, are we okay with this? We're going to plot this with more detail tomorrow. If you have any questions, we play with the parameters tomorrow. And I hope that everything gets even clearer. In the case of Poisson, if you have 4 events average per sample, what you expect is exactly that, is the average. And lambda has the same definition of the average number of the average count in the samples. Please.
Okay.
It's not working? Maybe again? Yeah.
Just to make sure that I'm understanding, in the Poisson distribution, as lambda increases, the curve changes.
Yes.
It becomes more similar to a normal distribution.
Yes.
Sorry, I'm trying to think how to express my question.
Okay.
But
no
then lambda is like what I expect to encounter, and then my y-axis is the probability of encountering what I expect, right? For example, I think you're going to explain it in a way that I'm going to understand.
So you do not expect all the time for like if you say lambda, but let me know if I'm not being clear. When you have lambda, you have an average expectation, but you know that this will not be necessarily what you encounter all the time. It's going to be something around this value.
Yes.
4 is an extremely high number. Like as I told you, like 0.5 is also a valid value for lambda. So sometimes you will have, in a plot, you have nothing. In the following plot, you have 1. And in the following plot, you have 2. And you have an average expectation. The average expectation, sometimes you have 3. But the value that you get most is 2, for example. Sometimes you get 1. There's an extreme case in which you have 5.
Okay.
So you have, of course, a distribution. And the average number that you have is what you talk about lambda. So it's an expectation around which the rest of the values are going to be distributed. If it's, and think about this, like if lambda is too small, the event is very rare. You expect more zeros and ones. You expect.
Oh.
This is why the shape goes like this. Because with lambdas, I imagine like lambda 0.5, what you get most are zeros and ones in your counts. Sometimes you might have a 3 and a 4. But actually, your expectation lies around this. Even if it's a number that is not a count. Even lambda can be 0.5, as I told you. So it's not that you're going to have half an individual in your plots, but it's the average number of individuals that you will have in your sample. If you have something that is more frequent, then lambda goes up. And the curve also starts showing a different shape because you don't have 0 as the most frequent value. You have values that are around lambda. Okay? So that's why the expected value, the average expectation is lambda, is the rate. Okay? Okay. I won't dwell again. Oh, of course. Come back.
Okay, now I understand what the Poisson lambda means, but I do not get why we have a discrete variable and then we have a parameter that does not give a discrete measure of that thing.
The lambda is not describing, like, why lambda is not a natural number, why it's not an integer. Because it does not need to, because averages work like that. You can have a binomial distribution of an outcome that has only two values, like minus 500 and plus 500. And your mean is going to be 0. Even if you never see 0 in your sample, it's your average. So you have an expected, and this is why central tendency values are not the only way to describe and are not enough, sufficient enough. So the expected values is not something that you will necessarily see in nature, not only for lambda, not only for Poisson, but for any distribution. And this is part of the beauty of the normal distribution. You will never have exact value because it's a continuous distribution, but you know around which is going to be the expected value. Is it? Do you want to add something? Is it okay?
I was going to add on that. I was going to just comment on that. Like in the Poisson distribution, so the x is the discrete variable. The lambda is just the parameter. It's there to give you the shape and the possibilities that x have, but x is the discrete one. You know, you have two parameters on your equation. One is discrete, the other is real.
It's the outcome that is discrete.
They don't interfere, they don't interfere in each other in this case.
You can have discrete outcomes with non-integer parameters, such as in every. Do you want anything? Is okay?
I will go back to the example of the trees in the forest, but if you
No, please, please.
think again about, for example, trees in a forest, and you can.
Have no idea.
It is. Yeah. Yeah. Sorry. So think, for example, again in the example of trees in a forest. So you can calculate the mean density of trees per square meter or per square kilometer, and this is a real number, larger than 0. It's a positive real number, right? So, but if you assume that trees are distributed randomly in the space, which is a very bad assumption, but anyway, Poisson will give you the probability of finding 0, 1, 2, 3, and so on, which are integer number of trees in a given quadrat area, for example. So lambda is, in this case, the density of trees, which can assume any real number above 0. But the number of trees that we will find in a given area of fixed size are integers. Got it? Makes sense?
It's a rate, yes.
I would just like to make a comment. We can take the example. So suppose that you know that, for example, you receive 5 calls in 1 minute. Now, in this case, lambda is 5. Is the mean of call that you can receive in per minute. So you will be interested to know what will be the probability to receive, for example, 1 call in 2 minutes, for example. And in this case, you know the parameter lambda, which will be the mean, 5, and then you put it inside. You have the sequence of number that you want to know the probability, maybe 0, 1, 2, and then in this case, you can calculate the probability of interest, which will be the number, what will be the probability for you receive 2 calls in 2 minutes, for example. And you can find it using the Poisson distribution.
Yeah. That's a great example. Because it stands for tons of rates. Like it does not necessarily stand for the kind of examples in the field that I'm saying. And you have, I think I will go on. Due to the fact that the expected value is not necessarily, not only due to the fact, but the expected value is not only one of the ways to understand the distributions. We also have to understand the variability around, the variability of these random variables. And this is not like in the case of discrete functions. I will not stay for a while, but in the case of Bernoulli, it's P times, it's P times Q. It's the probability of successes multiplied by the probability of failures. In the case of binomial, it's this multiplied by n, by the number of trials. And in Poisson, it's lambda again. So Poisson is this very interesting. I don't know if you, the fact that it's only one parameter for all these values is very interesting. Sometimes it can be used. Sometimes it's not necessarily useful. And I will stop here with the discrete continuous variables. They're, okay? And we will play with these parameters tomorrow. Okay? Any comments? Are you okay? So with continuous random variables, which are the ones that describe measurements, who are the key part is that these are impossible to count. You can have an idea of the sample space. You can have an idea of the outcomes. Or maybe you don't have. But you don't know exactly what is going to be getting, but also the exact value. The exact value only depends on the precision of your instrument, because there is not absolute value for any one of these. When you measure something with a caliper, with a rule, you have your graduations, the measurement scale of the instrument, and this is what you're going to get. Even if you had the most precise instrument in the world, you still would not get a definite value for this. Okay, so this is why we're going to be talking about, it's a continuous space. We are not going to be talking about discrete outcomes. And the random variable, now the probability density function takes lots of importance, because you will have a notion of how likely, how often will you have a different outcome. But you do not have, and you cannot read, the curves of probability as telling you the probability of anything. Since we are dealing with a continuous space, the probability density function will only show you the shape, but the actual probabilities is the area under the curve. The actual probability is the integral of this in a determined interval. So the total area under the curve of any continuous random variable is 1. And the specific probability of any single value that you measured, that you had the outcome, is 0. It's an irrelevant question. You cannot answer this. What you can do is doing this by tiny intervals, as in integrals, or to have areas under the curve of bounded intervals. Are you okay with this? In this case, there's an extension to this, is that you can have a cumulative distribution. You can have a cumulative probability distribution in which what you are counting is the probability that some variable is lower than the value that you are doing. So we also will have cumulative distribution functions for these random variables. They have to grow all the time. So what they do, if we have this example, imagine the simplest of the continuous distribution. Imagine, I will do the example with a random. So this would be a random, and this is the density variable. And this is why the functions in R are called D, because it's densities. Okay, even if, so it's D norm and D. You can have only the probability of tiny intervals that can tend to be very tiny intervals. You have the whole area under the curve sums to 1. And you can have at all times the probability that a given of having the probability that x is below to some cut point, like here. So you can have intervals. And the cumulative function, I will change colors, is going to be adding this area from the lowest point and adding the whole area. So we're going to see this in the lab. But what you have is, since even if you have lower distribution densities for some values, it's adding area all the time. And the growth stabilizes a little bit because you're increasing and never decreasing area, so it does not continue up. If you have a distribution whose shape is this, your cumulative distribution function would look like this. You're summing the distributions of areas. The simplest one would be a uniform random variable in which all the events are equiprobable. Any value, any outcome inside an interval has the same probability. We have a discrete distribution like this that can be help to think about this, is the throwing of a dice. A dice has 6 faces. The probability of having one face or the other is the same. It's 1 times the numbers of faces. But these kind of uniform distributions also exist in the discrete space, in the continuous space. The dice example is a discrete distribution, uniform distribution. Okay? And the uniform random variable only needs an interval to happen. And it's going to be rectangular because the area under the curve has to be 1. So you will have an interval between A and B. And you know that all the values are equiprobable, so you have a given distribution for all these. And you know that this area has to be 1. So what will change in different, oh, what did I do? What? You didn't tell me. So what you know is that different intervals of the same width will have the same distribution. And even like different tiny intervals will have the same distribution. And what will change is the height, depending on the interval. So if you have, for example, an interval that is 0 to 10, for this to be 1, you have to have a low curve that is equal to 0.1. It's 1 divided by this interval, okay? Because this area has to be 1. And this is the simplest probability density curve. So this is not an arrow. If you have a shorter interval here in the interval, this probability will change. So this, in this case, it's 1 divided the length of the interval. Okay? So just for you to picture, when we change shapes, the same holds. The area under the curve is going to be 1 all the time. And the probability is going to be the area of the interval. The expected value is still an average weighted average. But since we're talking in the continuous space, we're talking about integrals. Yes. So this has different like mathematical resolution. So you don't need to be knowing this as long as you know that what you calculate is the area under the curves. This is the probability. And we end up in the normal random the normal random variables. And this is the special case, and is the easiest and the most intuitive case for all of us. It's also called the Gaussian distribution. And it's going to be the basic for lots of methods. And the methods were developed assuming normal distributions. And later in the course, we're going to see how this stems up. Like other methods that were defined for normal distributions were developed by making special cases to other distributions. So you can have a linear regression, a simple basic linear regression will assume normality of the variables, and we will see this in a couple of days. But you can also have regression for specific different shapes of this distribution. So if you have a variable that follows a binomial distribution, you will have a special case of regression for this, okay? But the basic analysis is going to be all stemming from normal random variables. It fits many empirical data sets because normal distributions arise from the accumulation of tiny changes around the mean. And you can think about this, for example, if we talk about our height. You can imagine that we all have like an average height, humans, but the exact height that you have in your life is dependent on many different factors, including your genes, how you grew, lots of things that actually cannot be accounted for, that lots of times do not need to be accounted for. And these tiny deviations from the average are distributed normally because it's more frequently that you have of small variations around this mean than large distributions, large deviations around this mean. And this is the case with lots of variables. So, and the notation that Paulo showed yesterday is going to be this. We have two parameters, the mu, the mean, and the variance. Yes. So the expected value for this distribution is the mean itself, and the variance is the variance itself. So it's the square of the standard deviation. And it's cut, but it's in Paulo's slides. It has a shape that you already know, and it can be defined in terms of mu and the standard deviation mathematically. Normal random variables are very powerful because they can be transformed into one into another one. They can be displaced along the x-axis if you subtract the mean, and they can be rescaled if you divide by the standard deviation. And this is what we call standardization. And the standard normal random variable is a special case of a normal variable where the mean is 0 and the standard deviation is 1. Okay. And if you think about this, and this does not change the relationship of your variable. This does not change. It will rescale, but it will not change the relative ordering of your data. It will still be normal. And there are a couple of properties that I was going to talk about, but we have other continuous random variables. We can have log normal, for example, and log normal is a normal random variable that is skewed to the right, because what this continuous random variable means is that the logarithm of x is the normal random variable. And you can think about, for example, growth, proportions, growth, allometry. It's not normal, and you don't have values that grow in scales that are linear. You have values that grow in logarithmic scales. But when you transform them, the logarithms are distributed randomly, normally.
Okay. I'm trying to think how to phrase the question, but it's about transformation of the data transformation when I don't have data that is in a Gaussian distribution. I can transform it sometimes, but then like a little bit about the implications of how to interpret this data and how it relates to that other form of distribution, I guess. That's what I'm wondering.
I think this is not going to be happening a lot in this course. This is not necessarily the scope, like what to do, but you will encounter, yes, moments that when you transform your data, it starts complying with assumptions, for example, of regression. I will only say that when you do this, when you analyze, you have to remember that you did this transformation, that now you're dealing with values that have to be reverted when you interpret them. Well, there's a lot of literature about transformation, and there are different techniques, and you can see it, sometimes it's like, you can see like papers about do not do this, do not transform everything. And you have transformations that are not only applying one function, you can have a transformation that makes different decisions depending on what you are, on the shape and what you're maximizing. So sometimes it's more complex than only applying something. I would just say like, evaluate very carefully the need for doing this. Sometimes the fact that you have variation is not enough of a reason to transform. But if you do transform, you have to revert when you interpret. I don't know if Paulo, do you want to add something about transformation? I don't think we're going to do lots of transformation. Like maybe when we define the models, the transformation goes inside. Excuse me? Yeah. Okay. Sometimes what you do in modeling, what may happen here is that you know the variable and what you see. For example, the usefulness of log normal. You don't need to transform your data, but you model them. Like the fact that you model log normal instead of normal is already is how you understand the data. The fact that you're understanding that the data, the raw x's are not conforming to the distribution. Sometimes this is enough. It's a question of deciding how to model things instead of going and transforming and doing. Sometimes it works. Sometimes you transform and it becomes linear. A little bit what happened yesterday with the logistic example. You, Paulo obtained a linear regression by executing a simple transformation. It's not exactly. But what you do is you change the modeling way instead of applying a function without thinking about something that.
But like with log normal, and you said the example of growth. Like growth is not normal, and then you would have to make a logarithm transformation, so it would be normal. I'm kind of confused.
I think we're going to see that in later courses, because what we can do also is that the model itself uses an R distribution.
I don't think we're going to go through much of transformation use, because usually they're kludges, right? You're trying to take something that's not exactly appropriate for your data, and you're trying to make it fit into something that you can use, right? The log normal is a benign example of this, because you'll get the same inference if you actually use a log normal distribution. I mean, the log normal distribution has an expression, right? You can use the log normal distribution in your modeling directly. But if you log transform your data and use a normal distribution, you get basically the same inference. So it's kind of okay to do a transformation in that context. But usually it's better to actually describe your data using the distribution that you have, even if it's a complicated one. Instead of trying to transform the data, model it. Is sort of the ethos that we're trying to convey in this course. So we're not going to talk about transformations that much. But yeah, people use them, I won't deny it. But it's usually, what Andrea is saying is that if you do these transformations, you have to sort of go back into the original scale to interpret what you're getting, right? You can't do a log, a square root, divide by n, whatever, and then just use that weird transformed data that you don't know how it relates to your original data, right? But I guess the more like principled way of doing this is to actually model your data using more complicated distributions if you have to. But always work with the original data. Don't work with transformed data if you can help it.
Yeah, thanks, Diogo. And it should help, like especially when you're reading also, because you may decide not to apply them. But when you see in the papers that people transform their data, it should be clear what they did. Like it should be, it's part of you describing your methods and to be, and to come back to the scale. So when you navigate the literature, sometimes you get lost in these details, or sometimes you read quickly. But if there were transformations, they have to be justified, or they have to make sense. Not only because you want to fit, because you want to comply with the assumptions of a linear regression. Sometimes it's only because of that. but sometimes it's not necessarily super justified. Like, oh, we did a transformation because blah, and you stay like, okay, what? Like, I don't necessarily follow you. So this should, like, this knowledge, this first glance at distributions and other distributions should be helping also to read better, to read more carefully about what is being done. I think, okay, we still have 10 minutes, and we're going to be coming back to this, and we have two concepts, two mathematical properties of nature that are the central limit theorem and the law of large numbers that allow us to approximate variables to, for example, normal distributions when we have enough sample size. And that allow us to make some assumptions about the means of means representing the true population means that are the central limit theorem and the law of large numbers. The central limit theorem, is this. The central limit theorem, both operate at the same time, lots of the time. So the central limit theorem also starts operating because it's a limit. It operates when you have enough sample size. And this is why statisticians talk about sample size. It's not because more is nicer. It's because when you start doing measurements, the means of your samples, as long as your sample grows, it approximates the true mean of the population, of what you want to mean. So when we're talking about mu in the context of a normal distribution, of course, if you start with a small amount of samples, you can have averages that oscillate. If you add more points, and you add more points, your average will be approximating a value that is mu at the end. It's going to be an unbiased estimator of the mean of your population. And what we talk about unbiased, when we talk about unbiased, is because sometimes if you have a sample and you take the mean, sometimes it will be less than mu. And sometimes it will be more, but it's not going to be systematically more or systematically less. So if you make repeated samples of a population and you take means and means and means, it will be more, less, more, less, more, less than mu. But if you take larger samples of this population, they all will converge to mu. And this is the central limit theorem operating at the same time with a law of law numbers. So I don't have the basis, Roberto. So maybe, so people who have like more basis of mathematical, I have lots of trouble sometimes understanding when is one operating without the other. So the central limit theorem is about the means or means converging. And it also has a great extra result, is that the underlying distributions of some variables do not need to be normal. But they will still converge and have distributions that are normal. We are going to try to see this in the lab tomorrow. I don't have a mic for you, wait.
Okay. All the distributions we saw today, they have this, they tend to approximate a normal curve when you have a large n.
Poisson does this.
Poisson does this, but the uniform distribution, I do not see it.
No, it does not. No.
And the binomial distribution?
Also not, and it's discrete.
Okay.
But when you have different, we're going to see this in touch. We're going to touch this concept tomorrow, because sometimes you have different forms of distribution. I am talking about any shape of the distribution. If you have infinite, independent, it's the means that are going to be tending towards having normal distributions and converging towards the mu of a normal distribution. Yes. This.
I was confused because of that any distribution in the first topic. So I was trying to.
It's different shapes. Like this applies to different shapes of distributions, but there are so many distributions that I like. When I say any, I'm not talking about the three that we saw today, but given enough sample sizes, distributions tend to sum up towards normal distributions. It's. Please.
Just so I can understand this better, can I use a simple example?
Mm-hmm.
So if we were to try to measure the average height of this classroom, right? And we did this by selecting a group of people, bring them to the other room, and then taking the average of them on the other room.
Mm-hmm.
Are you saying that the average that we take on the other room is approaching the average of the classroom as we increase the number of people that go to the other room? Or are you saying that if we take enough samples, like of different people at random, the average goes to the classroom average?
If you take enough samples of if you take enough samples of a size that is good from, no, I'm not talking about this class, I'm talking about, you have to define your population, but this is a sample also. But different samples of our heights will converge towards our average. But we're talking about large numbers. Like different samples will also vary around the true population in a normal way. It's going to be random in the sense of noise. And the two things happen. Sometimes it's repeated enough, and sometimes it's sample sizes enough. Because repetition is sample size depending on the setting of the experimental setting. Sometimes you don't have very large samples, but your sampling effort is repetition. Paulo, you were saying, you were waving here, but that's okay. So this is why I'm saying that sometimes the one does not operate without the other, because the central limit theorem also needs large numbers.
Just a comment. As you have explained it, here we have a simple. So if you are interested in population, which should be the student in the graduation student of statistics in the public university of Brazil. And there you will take, for example, the size of each graduation class of each university. And you will calculate the average of each of them. And calculating the average of each of the graduation class of all the public university of Brazil, you will have the sampling distribution. The sampling distribution formed by the average of the age, for example, of all students in statistics graduation. So, taking more samples and forming the sampling distribution, you will converge to the real mean of the population who will be all the students of statistics in all the public universities of Brazil.
Mm-hmm. Yeah. And you get to define the population. We could be talking about humankind, like all the Homo sapiens on Earth. What? Homo sapiens, like people, humans.
I'm not getting what?
No, instead of defining the population as the students of a determined group, you can be talking about humans. I'm saying like Homo sapiens, I'm sorry, biologist. So we will be talking about this a little bit, and we have some examples tomorrow where it is by more sampling, repeated sampling, and some others where the size of the samples are going to be different. And this should let you have a grasp of how this works. So this is something that is the last slide of today, and we are so on time. So we will deal a little bit more about this and other concepts tomorrow in our code. Please let us know if you have any questions, comments. If there's anything that you still have comments tomorrow, you have still questions, we're going to be doing some exercises around these topics, but in code. If you have any problems using R and your computer, tomorrow we're not going to be using anything that is very difficult. We're going to be using the D and Q, some families of distributions that are already in our base. But for the next week, it's going to be good that you already have everything installed. So thank you.
Perguntar uma coisa. Inglês ou português?
Pode ser português, tranquilo.
Só mais.